So I volunteered to give a presentation today about Monty's current capabilities. I think it will be a good reminder to all of us and a nice overview to everyone new who joined, just to kind of get an overview of what Monty can currently do and also what it can currently not do. So we have realistic expectations and know what we're talking about and know what are kind of the next things we're thinking about and planning on, and where we have solutions and where we don't have solutions yet. I just put these slides together today, and I hope they won't be too confusing. There's a lot of content. So, I mean, there's like 3 years of content, and I tried to put them into a 1-hour presentation. So just interrupt me if you're missing context or not following what I'm saying. But yeah, hopefully this should give a nice high-level overview. I'm not going to go into the details of how the algorithm works. So if you want more details on that, we have some meeting recordings and the new documentation about that. So this is really just about the capabilities. Let me share my screen. All right, can you see that first slide?
Yeah.
All right, awesome. So what Monty currently can and cannot do. First of all, very briefly, what is Monty? It's not some magical wizard system, but it is kind of like this wizard. It's a sensorimotor modeling system. So you have a motor system, actuators, you have sensors that can move through the world, and then a brain that kind of processes all the sensory information, if you like to think of it that way. And we can have like different types of sensors and different types of movement through space. So for example, in our current implementation, we have something we often refer to as a vision agent, which is like fixed in space, and then the camera can kind of tilt up and down and left and right and explore the space like that. And then we have something we refer to as the touch agent, which is kind of like a finger touching an object, and it always moves perpendicular to the surface of an object, and it can like move along the surface of a cup and explore it that way. Monty has a modular structure, and no sensor sees everything. So we have sensor modules and learning modules. And it's not like how you usually think of it in classical computer vision, where you get like one picture of the entire object and then you recognize the object in there. But instead, we have like small sensor patches that move along the object and recognize the object through successive movements in space. So the system never sees this part. This is just for visualization. It gets this small sensor patch as input and movement information. And you can think of the sensor patch as like a small patch on your retina or a small patch on your finger's skin.
Good analogy is to think about looking through a straw.
Yeah. And that's quite a shift of thinking if you come from classical computer vision. That's something you kind of have to get used to, thinking about it in those terms. Also, models use reference frames. So for one, we get motor input and have motor output, since it's a sensorimotor system. But also the models are optimized for that kind of data. So they use reference frames to structure that incoming data. And they're kind of loosely modeled after cortical columns. So you can roughly think of a learning module as a cortical column where we have sensory input and motor input, and we have some kind of way to maintain a reference frame and store how features are located relative to each other in space. And then we have a cortical messaging protocol, which is a kind of a common agreement of how messages are sent between the different modules. So when learning modules vote with each other, that's all in a common language, no matter what kind of sensory input the learning modules get. So a column that gets touch input can talk to one that gets vision input. It can also talk to a higher level column or learning module. And it's all in that unified protocol, which makes it very easy to plug and play different modules and have cross modality information exchange. Does that make sense so far? That's the only slide I have on the basic principles. Okay, then let's get to the capabilities. So we have this project overview spreadsheet. I'll show it here briefly, where we kind of have a high-level view of the project and bigger tasks and ideas that we want to work on. And we have Monty, which is split into these different components like sensor modules, learning modules, motor system, voting, hierarchy, environment. And then we also have capabilities, and that's kind of the part I'm going to look at here. And whenever we get a task done over here and check it off, it will kind of add progress to these capabilities. So we can kind of see where we've put a lot of work in already, where we haven't done much yet, or we have a lot planned to do. And this presentation I kind of structured along these lines. So I'm going to go through each of these one by one and just kind of tell you where we're at, what we've done there so far, and what we can do on that capability. You might notice that none of the capabilities are at 100% yet. So everything can still be improved. This is still like this is a huge project, and it's not like we're anywhere close to having a general system that can do all these things perfectly, just as a front note. And yeah, I'll go through them one by one now if you don't have.
Are you recording this?
Yes, I am.
Okay, thank you.
All right, so object detection. Just again, as a brief disclaimer, how object detection works at the moment. So this is the evidence-based learning module. If you look back into the code later on, it basically tracks how much evidence we have for each hypothesis. So here we have movement through space, and after every movement, we take the sensation that we're sensing with the sensor patch and use it to update the evidence for different locations on different objects. And you can see as we're moving along this cup, we're kind of narrowing down the possibilities. So blue is low evidence, red is high evidence. And it's already quite clear that we're not on the banana or on the dice or on the bowl. But there's still quite high evidence for anything around the cup here. We're not sure where yet because the cup is quite symmetrical. And through more and more movements, we can kind of narrow down also the location on the cup. Once we actually get on the handle, we can be quite certain where we are on the cup. And over here, you can see like how much evidence we accumulated and what rotation we also think that the cup is in, because that's another part of the system. It doesn't only recognize what object we're on, it also recognizes where on the object we are and how the object is rotated.
Question.
Yeah.
So it says current most likely hypothesis is mug with rotation. Are the correct options, does it learn the correct option, or is it trying to choose from a set of correct options?
Yeah, so it has learned about the coffee mug. It has like an internal model of the coffee mug, but it could infer any rotation of this coffee mug. So when it first senses the coffee mug, it initializes hypotheses of what could be the rotation of the coffee mug given that sensation. And then the more it moves, the more it narrows down those possibilities.
But can it learn instead of mug, just cup or cylindrical? I guess my question is it like in classification, is it trying to choose from one of the correct 20 answers, or is it like actually thinking that
it's so in a lot of experiments, we use this YCB data set. So it has models of these 77 objects in memory. So it has seen all of these objects before, it has learned models of them. And then when it senses a new object and tries to recognize it, it basically has all of these 77 objects plus any rotation that these objects could be in. And then it kind of narrows down which object it might be in, what rotation it might be in.
Okay.
Does that make sense?
Yeah, maybe to.
Go ahead, Niels.
I was just gonna say, yeah, maybe it would be helpful to kind of clarify that Yeah, so at the moment, there's kind of this discrete list of 77 objects. And some of the stuff we've recently implemented is starting to capture more that like, okay, some of these objects are obviously more similar, like the different cups are more similar. But we have some ideas for how to kind of also consolidate that knowledge so that you could imagine it kind of, yeah, developing like a cylinder representation that would kind of come to mind. And so that it's not always like, oh, it's this exact cup.
We've actually, it's gotten pretty complicated because their teams seems to be the ability to sort of recognize objects using sort of different sets of attributes. You can recognize an object, well, sometimes we call it the morphology of an object. But that could be independent of the actual features of the object. So classic examples, you can have a face made of fruit, and you still see it as a face, even though the features aren't face features. And so and this gets into the problem of, well, you know, classification of categories, right? Well, what's a face, right? It doesn't have to have eyes, nose, it has to have things in the right position. So we spent a lot of time thinking about these issues about object modeling, and it's not just a unified thing. It's not just one model. It turns out that when the system's working, it says, okay, I have evidence for the orientation of a feature as a separate evidence what the actual feature is, and the models have to work with sort of in this gray zone between them. And we also haven't really quite figured out how we represent different classes of objects. We have a lot of ideas on this. We've spent a lot of time on it, but it's still an unknown a challenge, because we can clearly recognize things that are distorted and different and still know what they are. And the system has to be able to do that.
I guess the reason why I was asking if there's like a set of 77 or just thinking on its own, it's if we have like a Monty robot, an actual Monty robot, there's more than 77 objects in the world, so.
Right, it just learned them, right? It needs to learn these objects.
Okay.
So Viviane didn't talk about that, but you learn these objects through the same method of sensation and movement.
Right, so it can learn more than 77.
Oh, yeah, there's nothing fixed about the 77.
Okay.
Yeah, it can learn as many objects as you want.
There is an issue of capacity. I'm sorry. There's an issue of capacity of the individual cortical column or learning module.
Right.
And so that's another complicated topic we could spend time talking about.
Sounds great.
But yeah, maybe two quick asides on learning is like two kind of nice things about it is that it's does well with continual learning, and it just learns in a very kind of sample efficient way. So it's not like you need to, like in classic deep learning, where you need to like revisit an object potentially thousands or millions of times, and in like a batch, otherwise you forget about all the other objects. You could just kind of like add a 78th object. It could learn it after a few kind of passes over it, similar to a human, and then start using that knowledge.
Right, it's a good point. Really good point. There's no like training phase versus inference phase. You can mix them up, and as Neil says, you can continue to learn. You can add new ones as you go. Don't forget.
Yeah, and that's a very good point, because all the measures we have here, they don't really talk about the learning and how sample efficient it is, but that's one of the big strengths of the system, that you can learn a new object very quickly without forgetting anything about the already known objects.
Great.
All right, now some numbers. Object detection. So here, we have these 77 objects in memory. We already learned about them, and now we're trying to recognize them. And system does fairly well on it, not perfect. But here in blue is the distant agent. That's kind of like the eye that is fixed in position and moves, like tilts up and down and left and right. It's a little bit worse than the surface agent, which is kind of like the finger that moves along the surface. And the main reason for that is that with this fixed agent, there can be quite ambiguous views of objects, while the surface agent has a bit more flexibility of going completely around the object and kind of getting the whole size and shape of the object quicker. And then when we add noise and test these objects in random, previously unseen rotations, performance gets a bit worse. It gets less worse with the surface agent again, because it it can just kind of move around the whole object quickly. And then with using, so all of these numbers are with one learning module and one sensor. And then if we use 5 sensors and 5 learning modules and let them vote with each other, also again, noise and random rotations, performance is a little better than with just one. And I'll show some numbers later because voting is really a lot about cutting down on the number of steps. Not
That's
about
mostly what voting does. It lets you infer with fewer movements.
yeah.
So that's less about active.
Just to kind of give a bit more insight into these numbers. So we don't just have right and wrong as a potential result of an episode. We can also have the correct most likely hypothesis. That would mean we've moved along the object, but we have multiple potential hypotheses and we didn't get enough evidence to make a certain decision of which object it is or what rotation it is in the given maximum number of steps. So just to kind of keep experiments in a reasonable time frame, we have a maximum number of steps, and after that we stop and we just look at the most likely hypothesis that the system had, and this is the count of where the most likely hypothesis was correct, and this is where it was the wrong object that was the most likely hypothesis. And it can also happen that we actually classified an object, but it was the wrong object, not the one we saw. And here are some examples for when it confused objects. So it, again, here, I'm just showing these to give you an impression that like when it fails, it is a bit kind of understandable of why it fails in a sense. So for example, here it mistook spatula for spoon or fork for a knife, or A toy airplane for B toy airplane, which are, yeah, kind of similar objects in morphology. And then when it has like the most likely hypothesis confused, it confuses Phillips screwdriver for a flat screwdriver, but they were both still in the hypothesis space. So if we had moved more, it might have figured it out, corrected itself.
Are you going to talk about action policies, Vivian?
Yeah, briefly.
Okay.
Yeah, it might be worth just briefly mentioning on that because I was just reminding myself. Because yeah, I think at the moment for all of these main experiments, including like the 77 objects, the distant agent can still go to other sides of the object because they now have the so there's a policy that kind of called like the hypothesis-driven policy where the learning module will kind of have its internal model of what it thinks is the most likely object, and then, for example, it'll have another model of another likely object. And yeah, I guess maybe you'll talk about this, but
yeah, I'll show a
anyways,
figure on this.
okay, cool. So,
Yeah.
but so just in case you guys are watching this video later or something, in terms of that difference in accuracy versus the distant agent and the surface agent, partly as well, it's also like there's subtle differences in how they move, even though they can go to different parts of the object. Like the distant one is a little bit more of a random walk, whereas the surface one is a bit more of kind of purposefully moving along the surface. And so it's that small difference is potentially just down to like, not getting like if it's not converging quickly, then it may be more likely to just accumulate a lot of noise and things like that.
So I don't know.
Yeah.
Go ahead. Sorry.
No, I'm done talking, but I just wanted to clarify that in case anyone's watching this later.
We started this, we didn't have a sort of any kind of sophisticated action policy. We just moved along surfaces. Of course, if you were presented with 2 screwdrivers, you wanted to know which was which, you would immediately know where to look. You would look at the end of the screwdriver and attend to that point, whether you do that with your finger or whether you do that visually. And so there's a more intelligent action policy to differentiate objects. And so, but in the beginning, we didn't do any of that stuff, right? And I'm not sure where we ended up on, but we do have more sophisticated action policies than we started with, which in the beginning was like, there's no action policy. But this is a big part of getting, the differentiation of objects is to know that, between these 2 objects, in fact, where I have to attend to tell the difference. And we do that all the time.
So speaking of action policies, actually, I had a question while reading the TBP document. Like a little, I didn't go through the whole thing yet in one day. Just the first part where I think we do a good job in distinguishing Monty, that it is not your classical computer vision or supervised sorting problem that we're trying to solve. And I guess I was wondering how, maybe we need to clarify like how different it is from RL, I mean, especially because we're talking about policies as well. So, are we learning policies? So will Monty learn, okay, if I have these two screwdrivers, the intelligent, will it learn on its own that?
Yeah, so yeah, it'll be kind of a mix. So like the policies we have right now can be considered kind of innate policies. And
Well,
but yeah,
yeah,
but we'll definitely have elements of reinforcement learning as well.
even now we have policies where there's learning involved. So we have the model free policies that are basically you just get the sensory input and that decides how you move next. But then we have the model based policies, which are we call the top down policies, where you learn the model of objects and then you use that learned model to decide the next action. And I mean, we're not saying that reinforcement learning is like at odds with the system. So for example, you could use reinforcement learning as for the motor system and train a reinforcement learning agent for the motor system part of it. It's just that here we're kind of setting the framework for it, where we also have these models that we learn using reference frames. And we're not using like deep reinforcement learning, which is not very sample efficient, for example.
There's a tendency, pretty much everyone, to think about Monty in terms of what they've learned about machine learning in the past.
Yeah.
And almost always that's wrong. Okay, you just have to really start rethinking things, you know, the sample efficiency, the whole reference frame, the integration of movement into the whole thing. It's just really, really different. And you have to be careful. That's the hardest thing to be successful at Monty, is to realize that we don't want to be constrained by the way we think about things in the past. It doesn't mean that the brain doesn't do reinforcement learning, but you're just not going to drop it in and say, okay, we're going to solve this problem with that, you know.
And then yeah, one other. Oh, go ahead.
Well, I had a couple of questions. I know we have a lot to get through. I don't know. I think we have time for
Yeah,
it.
go ahead.
Sure. So when you do these object detection things, are we looking at like a fixed number of steps? Is it allowed to terminate itself once it gets to a certain confidence level? And
Yeah. So
I guess my question on that front is that what if the object, there's a brand new object and it looks like 90% like another object, but it has a new distinguishing feature? Like, how do we prevent it from terminating itself too early before it gets to that new feature so now we're looking at a new object that has to learn?
yeah, so there is a terminal condition that is basically saying, oh, this is an object that I don't know about. So it is not forced to choose between the 77 objects. It can say, oh, this is a new object, and then it would learn about that object and create a new model for that object. And next time it should be able to recognize it. But if it is the case, like you say, where you're moving along the object, it all matches with a known object, and we never get to that different distinguishing feature, then yeah, we would recognize it as that known object. I mean, it'll be difficult to prevent that. I guess we would have.
You know, if you've never observed it, how would you know? Like,
I'm just thinking if I were to maybe grab these headphones or something and they had been swapped out slightly differently, maybe the very first grab, I'm satisfied that these are my headphones.
right,
But maybe if I grab on the other side, I feel something that's like brand new.
right. But you know,
Maybe in reality.
in your old headphones, you've explored the entire object and you know what's back on the backside. Then you'd see something's wrong. You'd have a model and the model makes an incorrect prediction. You go, oh, that's not right.
Right.
But if you've never observed the backside, how would you know, right? You know, it's like you just wouldn't know.
Yeah, I mean, at the moment, basically, we don't have a condition to handle that. I think there's a lot of stuff we want to improve about the kind of unsupervised learning aspect, in terms of how you basically kind of naturally add on more objects without it being kind of like there's also the issue of kind of like how do you learn in like a multi-object environment, and you know, how do you know, okay, now I'm on a different object. And I think all of these things are related to kind of concepts of like prediction error and surprise, and like, you know, okay, I thought I knew what object it is. Okay, clearly something's very wrong. So now I need to take a step back. But yeah, it's not something we have implemented at the moment.
But yeah, and I get into a lot of these topics in a moment. So yeah, just for the sake of getting through the presentation, maybe
Yeah.
I'll. Yeah.
Right. I guess just one quick thing I wanted to mention about the policies to your question, Soji, was just yeah, although a lot of these policies that we have right now are kind of intrinsic, the other thing and kind of being designed by us, the other thing to I guess emphasize is that they would also apply even in more kind of abstract spaces. A lot of these ones, like the following principal curvature on an object, can have kind of parallels in abstract spaces, and also the hypothesis testing one. So like we're not just kind of going to try and design all policies that something might need to recognize physical objects. This is still kind of like a long-term, I guess, plan with these policies.
Yeah, I guess I just don't want other people to come like see Monty and it's like, oh, I guess it's just another RL system. It's not, right?
Right.
It's much more.
Yeah. Right. But to your point, yeah, we can maybe emphasize that a bit better.
Yeah. So yeah, and just to make it clear, right now, all these results, like none of them use any kind of deep learning or reinforcement learning, even though we could use it in places, but we don't need to. Okay, let me just show you. I mean, I just showed you the results from the best one, now just from the worst one. So this is the distant agent with noise and random rotations. And here you can see there are just a lot more cases where we reached a timeout condition. So it's just not confident enough to kind of terminate the episode and say, I'm on this object. Most of the time, it still has the correct most likely hypothesis. And then again, there are a couple objects that it is confused about. But again, you can kind of see that all the ones where it's confused are like very similar objects, either morphology-wise or color-wise or both.
Yeah, we shouldn't view this as a failure of the system to recognize it. You know, you've got your count of 40 steps there. If those 40 steps are all local on the object, you're not going to figure things out. It goes back to the action policy and how do you efficiently sample the object completely. There's a lot going on there. So
yeah,
these incorrect things were natural given the way that way we set up the action policies and the sampling.
Yeah, definitely. And that's why I'm saying there are a lot of points where we can improve more, and we have a lot of concrete ideas of how we can do it. We just need the time and resources to implement all these things.
Hey, Vivian, did you run an experiment where there was an unbounded number of steps to see what the correct percentage was?
Yeah, we did, but I don't have the results by hand right now. But it would be pretty easy to rerun it if you're interested. All right, now pose detection. So this happens at the same time as object detection. It's kind of the same process, actually. And this is the rotation error in degrees. So just for you to kind of have an idea of what those mean, I put these little icons here. So this basically means if that would have been the correct rotation up here, then this is what it would have detected on average. It is, again, better for the surface agent than for the distant agent, and better without noise than with noise. But all of these, I think, are reasonable. The 5 learning module condition is actually not very good, but again, there's another action item we have on the agenda. Voting right now is not happening on pose, but only on object ID. And I think once we incorporate that, that should also help a lot here. And then another note on that is if we actually look at the distribution of rotation errors, it's a bit of a bimodal distribution. So there's a little spike here at 180-degree rotation error, and that's essentially like mirror symmetry. So a lot of objects in the data set are symmetric along 1 or 2 axes. So like cups and dice and all these kind of objects. So we do have a symmetry detection in the algorithm and kind of account for it, but doesn't always catch it. And in those cases, we get a pretty high rotation error, which kind of skews it up a bit more.
One thing that's really useful when you think about these experiments, like you think about the surface agent, imagine you sticking your finger into a black box, you're touching something. If the cup is completely upside down, you might at first think it's just a cup, and it takes a little bit more effort to realize the cup is inverted. Then you might touch the handle, you might touch the side, until you actually put your finger on the top, you don't know. So that's just, you can always relate this back to personal experience, and it's very helpful, I find, to do that when you're trying to figure out why does it get this error. Just imagine like the thought experiment, and you'll be able to see what's going on.
Yeah. And then, yeah, here you see another example of the symmetry case happening. So we have the target here, this dice, at this rotation 90, 0, 180, but it actually detects 90, 0, 0. And if you look at the image, it's like almost identical. There's some artifact down here that maybe distinguishes it, but it detects this rotation, plus it detects that it's a symmetrical object. So we would count that as correct. And it's actually good that the system doesn't kind of overfit to these little artifacts down here on the dice. Next one is number of steps. So how fast do we recognize it? And there are kind of two approaches we take to cut down on the number of steps. One is voting and the second one is policy. So voting is we have a bunch of patches. In this case, they all move together in the same way. They could be moving independently, like 5 fingers on the hand, for example. In our case, they don't. They just move together over the cup like shown here. Each patch feeds into a different sensor module, and each sensor module feeds into a different learning module. And since they all get different sensory input, they might have different hypotheses about what object they're on or what pose that object is in. But then they vote with each other and can kind of thereby narrow down those hypotheses much faster together. And if you look at the number, it cuts down the number of steps required by more than half, quite significantly, and it slightly increases accuracy.
Again, you're not voting on pose here, right?
Yeah, right. And that's something we need, that's not fundamentally
has to be done.
possible, we just need to add it.
Have to do it, it's tricky.
Yeah.
We don't know how it's done the right thing, so. But we know it has to. So.
Second way to improve number of steps is the policy, like we already mentioned before. So for example, this touch agent has the policy that follows principal curvature, and then it changes to follow the different principal curvature, and at some point it changes again to follow orthogonal to that, and so on. So it is kind of a bit more directional about where it goes, and explores the object more efficiently than it would if you were moving randomly on the object surface. And that helps a lot, like Niels mentioned earlier. Second
And
one
maybe
is,
it's worth us just quickly defining the principal curvature. So like if you imagine the like side of a cup or like a cylinder, you'll have like the maximum magnitude of curvature, which would be like going around the cup. And then the orthogonal direction to that is the second principal curvature. And in a cup that would be flat. Like there would be no curvature there.
yeah, so on this cup, the flat one would be in this direction, and then the curved one would be in this direction. And principal curvatures are always they're always orthogonal to each other, so they kind of span up a reference frame together with the point normal, which always points out of the surface. Should have made that clear. Yeah. Yeah, the second type of policy is the top-down or model-based policy. Those are based on the models that are learned in the learning module. And one that we use at the moment is this hypothesis-driven jumps. So basically we have two hypotheses, in this case, a fork and a knife in these rotations. And then we look at where should we move in order to distinguish these two objects. That would be the red point here, and then we would kind of jump with the sensor to that location and sense there. Here's some example. We are first following the principal curvature, and then we do a jump to the top of the cutlery, since the handle is not very distinguishing. And then that should narrow down our possibilities quite a lot. Or here with 5 learning modules, we can, and a distant agent, we can also jump to different locations on the object.
I haven't seen that figure. It's cute.
Yeah, Niels made those. And again, that cuts down quite significantly on the number of steps we need to recognize an object.
So it seems like you would start with a non-model driven action policy until you have some hypothesis, and then you quickly switch to a top-down one. That's what.
Exactly, yeah. That's what's happening here. First, we follow the principal curvature, which is not model driven. It's just based on the sensory inputs. And then once we have some hypotheses, we do a jump.
You can imagine again the finger in the box. You have no idea what you're touching. You follow some edges until you say, oh, that might be this. Then you make a jump to hypothesis, see if it is correct.
It's also interesting on this animation that like you have your high confidence about the rotation of the object. You're not sure what it is yet, but you're very sure it's like lying along this plane. So your hypotheses are like almost overlapping, which gives you greater confidence about how to use the hypothesis to move around the object.
Yeah.
And like again with the symmetry, like it'll sometimes kind of fail in that like it might suggest going to the other side of the cutlery, but like it's not really a genuine failure. It's just like it can't know until it tries to sense one of the tops, like which way it's actually oriented in space. But yeah, and so that's like another thing where we have some ideas for how to do it, but like at the moment when we go to an empty point in space, that doesn't update our hypotheses. Instead, we just make sure we move back onto the object, but it would be very natural for us to integrate that into the system so that like feeling empty space does tell you a lot about, you know, what is the orientation of the object and things like that.
Yeah, it's very good to know where the object is not. And yeah, that's a nice thing that it just comes kind of naturally out of the system and how we do things, that these hypotheses will align with each other, and you don't like the models for fork and knife might have been learned in totally different orientations. But then once we use the hypotheses about how they're oriented, they will be automatically aligned and we know where the most distinguishing features would be. So now on speed, efficiency, obviously that's a bit related to number of steps, since less steps means it takes less time to recognize the object, but this is really more about like how long does each individual step and hypothesis update take. And I'm not going to go through these in too much detail because those are kind of a bit older numbers. I just pulled together slides from the past 2 years. But we've already done a lot of stuff on speed ups, so including just kind of vectorizing a lot of stuff, testing only the top K hypotheses, using different libraries that are faster on our infrastructure, using multiprocessing and multi-threading, and that kind of helped us get a lot of speed ups already. This is kind of the current setup. So we vectorize the evidence update. So those are all matrix multiplications and matrix operations. We use multi-threading for the loop over learning modules, for the loop over objects and memories. And then the loop over learning modules could be parallelized, but is not at the moment. You'll see that in the speed numbers. That's kind of one of the bottlenecks if we use more than one learning module. And then we parallelize episodes in an experiment during evaluation. During training, we can't do that because when you're training and learning and constantly adding new information to your models, obviously the sequence matters. So we can't do that in parallel during training.
Yeah, maybe it's worth mentioning, like at the moment we tend to have a lot of objects, like up to 77 objects, whereas we mostly have one learning module, maybe 5. And so that was the reason for kind of choosing to parallelize over objects. But of course that might start changing as we want to add learning modules, and then sorting that out would be more important.
Yeah, right. And then, we also did some analysis on what the slowest operations are now. So currently the slowest thing is a KD3 query operation, which is basically if we have a hypothesis of where we are on the object, that location usually doesn't exactly correspond to a location where we have stored information about, like in the object's model. So we have to kind of do a nearest neighbor search to find the nearest points in the graph stored. And that search takes the most time. We have looked into alternatives. We have tried alternatives, but we have not found anything faster so far. This
is an example where it's really interesting. I think I know how neurons do this. And it's not a separate step, it's very efficient, it's really kind of clever, but it requires, the neurons do it using synapses and they're locational on the dendrite, and it's a completely different mechanism for how it achieves the same result. So it's the kind of challenge we face in this system, right? Here we're trying to do it, not emulate neurons exactly in their details, but when we don't, sometimes you run into issues like this.
Yeah, and this might be one thing that we could maybe solve with a more biological implementation at some point.
Right, but then that requires putting a whole bunch of other biological details in to support that. So it's an interesting challenge. That is one of the big challenges of Monty, is to know where you put the dividing line between, and I hate using the word neural inspired, so neurally constrained solutions, like, this is how the neurons do this, and we don't want to emulate everything, and yet where do you put that line? It's challenging to know.
Yeah. And then, the second slowest operation are just matrix operations combined. We already managed to cut down a lot on this time just by only testing the top most likely hypotheses, or only updating the most likely hypotheses. We can make the matrices much, much smaller and make it much faster. And then just some numbers again. So this is runtime per step with 77 objects in memory. A lot of our smaller benchmarks only use 10 objects in memory, and that's faster as well. And this is on 16 CPU cores. If you use more, you can also, of course, make it faster or slower if you use less, or on the laptop, it's also faster. But yeah, here under the setting, just to get some relative numbers, it takes around 2 seconds per step. It takes pretty much exactly 5 times that amount for 5 learning modules, because as I mentioned earlier, we don't parallelize the updates of learning modules, which we could do somehow at some point. But then if we take the total episode runtime, so total time taken until the object is recognized, that difference isn't 5 times anymore, just because 5 learning modules take less steps to converge. So they just recognize the object faster. And yeah, it takes about 2 to 7 minutes.
So the left chart is seconds, the right chart is minutes?
Yeah, this is seconds, this is minutes. It's still not as fast as we would like it to be, but yeah, this is current numbers. All right, noise. So there are 2 places, there are 3, but 2 places that we commonly test where you could inject noise. We can inject noise right here onto the data, the raw data goes into the sensor module, or we can inject noise here onto the data that goes from the sensor module into the learning module. Third option is injecting noise into the models directly. Basically, this one tests how robust the sensor module is, and this one allows us to test more controlled how robust the learning module is. Here's an example of how noise looks like if you add it before it goes into the sensor module. So you could imagine like some noise added to the RGBD image, and then kind of all the estimates like of curvature and point normals just get skewed quite a bit. And then if you add noise here, you can add it more refined on specific features, like just noise on the location information, or just noise on the color, or make it more or less noise on different kind of features. Here's just an example of the typical amount of noise we add to the locations in all the previous experiment results that I showed, where it was the noisy conditions. To address this raw noise, we added some better calculations, some robust calculations for the point normal. That was the work that intern Jad did last year. So we got some improvement, quite significant improvement there, just using more robust point normal estimates. And then another thing that comes out of the system is this ability to switch to use different modalities. So I just threw it in here with noise because it seems a bit related to noise. If basically this is testing, we learn an object with a touch sensor, put the model in here, and then we unplug that sensor module and plug in a vision sensor and try to recognize these objects. And we pretty much get the same performance, slightly higher rotation error, pretty much same amount of steps needed. One thing to add here is that our sensors are pretty similar here. Just the action policies are the bigger difference. That's that. Did you have a question, Will? It looked like you were gonna say something.
I was shocked and delighted by that works. That's crazy to me that you can plug in a different sensor and it's still recognized. Is there anything out there in deep learning world that can come close to doing that? It seems shocking.
Yeah, I'm not aware of anything where you can just do it like plug and play like this. That's definitely one of the big strengths of the system. For one, you can just plug and play sensors as long as they can all like estimate movements in space. You can at least generalize the morphology of objects. Obviously, if like you have a vision sensor where you have color and then you use a touch sensor that doesn't sense color, you can't like distinguish a blue from a red cup anymore, but that's like impossible. But the features that are still there, you can just generalize very easily. And then the second thing is that you can also do cross-modality voting and communication, like with pretty much all deep learning solutions I know about. It's like there's different sub-networks and you have to kind of coordinate them somehow and merge the features into like a mixed vector or something, or mixed embedding, whereas here you could, like, they all use the cortical messaging protocol, so it's very straightforward.
You know, this goes back in history of neuroscience again, you know, where Mountcastle said, and other people say, hey, there's this common structure throughout the, cortex is repeated over and over again. The same processing is recurrent everywhere, every point in the hierarchy and so on. And neuroscientists didn't believe it either. So many neuroscientists says that how can that be? It doesn't make, it looks like it, but it can't be true. And that maybe, well, your comment as well. The key to understanding all this, of course, you just have to accept that it's true, and then you figure out how it works. And then really the key to understanding it was a whole bunch of things we've talked about. The fact that it's sensorimotor, and each module knows about movement and the build reference frames, and then the voting, all this stuff plays together to allow that to happen. But that's one of the key elements of this. And we think about the future of Monty and Thousand Brains Project. People are going to build these modules in silicon, and they're going to be identical. And you can plug a lot of these modules, and you can hook them up to different types of sensors in all different types of ways. And that's what we see in biology. Mammals have different types of sensors. They all feed into the same cortical learning algorithm. They all seem to work. All animals seem to function, all mammals, and yet they have the same underlying thing, even though they have different sensors, even eyes are different. And some, animals have electric sensors and things like that. So we just have to accept it's true, and we have to make sure we understand how it works.
Can I ask a quick question, Viviane? When you're saying you're having difficulties in accelerating the nearest neighbor search, did you guys try locality sensitive hashing?
Yes, I did. I'm not sure anymore what the problem was with it. I would have to go back into my notes.
Okay, because effectively it creates a dimensional reduction so that jumps you to the most likely candidates more quickly. So, but sometimes you got to do multiple hashes in order to get enough specificity.
Yeah, I just remember there was something. It was either like learning became massively slower or something like that, or there was some issue that we had when you looked into it.
Yeah,
I don't remember the details.
Yeah.
It seems like if you're using KD trees now, that it could be a swap-in thing, but that's just my naive conclusion from what you presented.
Yeah, I'll have a look back in my notes what the problem was back then. Maybe it's something to fix.
Yeah, I mean, at least I'd be interested in what the problems were, because we're looking at that on our side of the thing too as a possible accelerant. And if there's inherent problems with it that Monty's seeing, then it would be good to know.
Yeah, I'll have a look back. Okay, let me move on. It's a lot of stuff. I hope I can get through it. All right, unsupervised learning, like we mentioned earlier. The idea is learning and inference is really a very intertwined process. And although right now, a lot of the experiments we run are just evaluation, we still think of the system eventually just working continuously, learning, recognizing, learning, recognizing. It's like to do any kind of learning, you have to do inference at the same time all the time as well. So for example, here you're moving along the cup, you recognize, oh, this is a cup. And then you move some more, explore the object some more, and add these new observations into your existing model of the cup. And so you keep learning and adding onto your models. And we want to be able to like continually update our models of objects. Here's a more concrete example. We have a model of a banana, and we recognized the banana, and then we explored it some more and added some new points to it. And obviously, we also like make sure we don't add redundant points into it. But that's the basic idea. And we have a couple of experiments in our benchmark test suite on this as well. We don't get great performance here yet. And I think this relates mostly to what you touched on, Scott, that like if we have very few objects in memory, like just one or two, it's very easy for the system to like confuse objects. They are not as disentangled yet. So for example, it merges a model for mug and cup, or a model for strawberry and golf ball, or a fork, knife, spoon object usually emerges. And then once you have this kind of merged object, all the following episodes just kind of recognize these merged objects and add points to them, which is
I guess partly that's like a symptom of the data set, or like the benchmark as well. Like we kind of want the mug and e-cup to be merged, at least at some levels of the system, and that's also something we're working on. Like in some ways, it's kind of great that it confuses or like thinks these are the same thing and merges them into one.
Well,
Yeah,
we also
and
need to be able to need to fork those at some point, right? If it's important.
Yeah. So what we really need is like a hierarchical data set where we can say like, okay, does it recognize it at the granularity of like the most precise object, like fork versus spoon, or does it recognize it at the kind of granularity of like piece of cutlery, or does it recognize at the granularity of like cylindrical object?
yeah, and what this really probably boils down to is like a learning parameter of like how high do you set the threshold for recognizing a new object, and that might be something that just has to kind of get higher, like, or lower over time the more objects you have in memory. Something like that. Like if you only know one object so far, it's very likely that the next thing you see is maybe a new object and not just that object again. So yeah, not an unsolvable problem, and actually kind of a desirable property of the system that it kind of merges these also correctly oriented and aligned.
It's also kind of currently, I guess, only using like bottom-up signals to detect when it's on a new object or whatever. Like there's no, for example, like scene level understanding or like object permanence. Like we could definitely add that with the hierarchy, but like, yeah, so that it understands like, okay, I'm moving away now. Okay, now it's going to be a different object, and things like that. But yeah.
Yeah. Talking about multiple objects, now we're getting kind of into the newer parts and the capabilities that are a bit lower on the progress bar. So Niels implemented this multi-object environment, and that's what we've been testing on so far, where we just kind of put a bunch of objects into an empty space. We also have some more evaluation criteria or measures now, where we can have a primary target, the object we start on, but then once we move on to a different object, then obviously we have a new target that we want to recognize, or we want to go back to the primary target. And these are also some results from last year that like we can use the shift in evidence that we get when we move from one object onto another object to detect that we are now not on that object anymore, and kind of use that to move back on the object or reset our hypothesis space. And those are some initial results, and Niels is picking up that work again now and kind of, this is not really integrated in the current code yet. So this is kind of work in progress that I'm showing here. But that's the general idea. Categories and generalization, also another topic we talked about briefly now, but just some experiment we ran here is that basically I took the memory, the 77 objects, I deleted one object out of memory, so I would delete the cup out of memory and then see what other object it recognizes instead now that it doesn't know about the cup anymore. And that's the object always shown on the right. So instead of a cup, it would then recognize the red cup instead of a mug, or instead of an orange, a peach, or instead of this one, or instead of a spoon, a knife. As you can kind of see that this is like pretty much always the most similar object in the data set that's remaining. And of course, there's a lot more we can do on categories and generalization, but first we will need some new data set that actually has categories of object and new measures on testing that. Another one is, I'll just go through this quickly, but like if you cluster the internal representations of learning modules, you kind of get these clustered into nice clusters that kind of express also the similarity of the objects, even like first the morphology, but also in color space. And this is a plot from Rami. Also, if you use TSNE to put all the objects on a two-dimensional space, you can kind of make out some meaningful clusters of cups and ball-shaped objects. And then another thing we've implemented but still need to do a lot of testing on is like adding more constraint graphs and graphs that kind of update over time, and where you can learn through those constraints, you can learn more generic objects with like only the features that are consistently present. So you like learning a generic cup shape versus this specific cup that has a dent in the right corner. Then compositionality is also one we've done a lot of brainstorming on the past year, and we have a lot of concrete ideas also of how we want to implement it. We have the basic routing implemented and some first like Monty setups and experiments implemented, but we don't really have a good data set for it yet to test. Rami's internship work tied into this as well, encoding object IDs with some kind of similarity measure, so the higher level learning module can kind of meaningfully interpret these features. And then this was our hackathon project in the summer, to put together like a scene data set where we can actually test compositional scenes where we have lower level objects, so fork, spoon, knife, plate, and then a higher level scene that's composed of these objects relative to each other in a certain arrangement. So now the next step here is basically turning this into a benchmark experiment, adding some measures of performance in there, and testing how well our current implementation does on it. Deformations is something we have no clue on right now, I would say. Something that comes up every once in a while, but I don't think we have any really promising lead on how to implement this or deal with this. At the moment, all the objects we recognize are like solid objects, not like a t-shirt that can be deformed in a bunch of different ways. But it's something we need to think about more and figure out how to do. Different features on the same morphology. So we have the morphology of the cup, for example, it can have different color, different pattern, can have a logo on it. Or similarly, same features on different morphology. So you can have the Numenta logo on a cup, or the squishy brain, or a baseball cap, and we can recognize it on all of these. This is something we've done a lot of brainstorming on lately, and we have some ideas on this, but nothing implemented yet. Scale, you can have like a children's chair or an adult's chair, or if you live in Germany, maybe you've come across this furniture store that its trademark is that it has a giant chair standing in front of it, and you've probably never seen a chair this big. They actually, I think, have the world record for the biggest chair, but you have no issue recognizing it. So like at the moment, our system would not be able to do this. We have some ideas about how this is done in the brain, but we have yet to translate that into an actual implementation. Real-world sensors and agents. We've briefly dabbled into this one during a hackathon like 1.5 years ago, where we took the iPad camera and wrote a little iOS app that would basically take a picture with that iPad depth sensor camera of whatever was in front of the camera, and then we would have like a little patch out of that picture that moves over it. So it was kind of 2.5D maybe. And we would then actually recognize these objects. And that was the first real-world demo of Monty. There's a recording of it as well. It's kind of a cool moment. And in that project, we also made a data set where we have this kind of set of real-world objects that are all at Niels's apartment right now. And we have 3D scans of all of them, so we can test them in simulation, or we can test these actual pictures that we took under different conditions. So here you can see the sim to real transfer. We have some performance drop, but it still works. So, above chance, like significantly above chance. I mean, there are like 12 objects in here. And then some more adversarial conditions, like where it's dark or very bright with a lot of reflections, hand intrusion, or multiple objects. And yeah, there's still a lot we can do to improve these numbers, but we have at least a small data set to test on. Object behaviors, again, something we've done a lot of talking and brainstorming about, and reading other papers and thinking about how we might solve it. And we have some ideas of how we could implement a solution to it. And Jad, an intern, implemented this little toy environment where we can set up some kind of very simplistic objects with behaviors to test solutions on. But the current system can't deal with object behaviors yet. Achieving goals. So this is on the policy part. So if you actually want to put the world into a certain state, how do you tell that to the system, and how does the system then move to achieve that state in sense? Again, we have some ideas on this. One thing we did implement is the goal state generator, which is part of the learning module. And that one can take the models in memory, the current hypotheses, and whatever is currently being sensed, and use this information to generate a target state and send this to the motor system, which can then translate that into an action. And we, for example, use this goal state generator for the top-down policy to tell the motor system where to move to resolve ambiguity, like what I showed earlier with the knife and the fork, telling it to move to the top of the knife. And then we also made some plans of how we might set up some more test environments to test kind of goal policies, where we have a certain goal state that we want the environment to be in, and then we have the state the environment is currently in, and it has to figure out in various adversarial conditions of how to get to that state. And then some plans on how this would look in the whole system. One requirement for actually implementing and testing this will be the modeling compositional objects. So kind of solving that dinner set table scene and recognizing these scenes will be something we need to do first before we can tackle this. Someone just started sawing outside, so I'm gonna close my window.
We didn't hear it. I didn't hear it.
All right, these are a bit quicker because we don't have actual numbers on it yet, so maybe I'll get through everything. Abstract concepts and spaces, n-dimensional spaces. For one, we have the temporal dimension, so object behaviors or melodies, things like that. We have the classical 2D space, like grid cells. Then we have three-dimensional objects where we know a lot less about how the brain represents those reference frames. We have more abstract spaces like family trees, which might be like a subspace of 2D space with more constraints on it. A very abstract space like math. And then like four-dimensional space like quaternions, even though I'm not sure our brain is actually equipped to deal with these, at least from my personal experience.
Yeah, like I think we're generally dealing with the assumption that brains can represent 3D reference frames plus maybe a temporal dimension, which is maybe why quaternions are impossible to understand
Well,
Yeah.
for
it's
at
also-
least most
It's
humans.
also possible that, I've always viewed it as one possibility is that the quarter of a column or a learning module, the algorithms we think underlying it might suggest that they could learn n-dimensional spaces. The neural mechanisms suggest that. But early in our lives, we don't experience certain dimensional spaces. And if you don't, and then they become kind of set. That's the part that doesn't get changed a lot in your lifetime. And so, because everything else is built upon that. So if you didn't experience those as a child, you wouldn't develop representations for it. You couldn't do it later. We see that with math, right? If you don't learn math early, it becomes very, very difficult to understand math concepts later in life. A lot of things are like that. Music is like that. So it's possible that the underlying algorithms are capable of learning n-dimensional spaces. But once you've learned whatever dimensions you're working with, you don't want to change it. Because all the models might get really screwed up at that point. So I don't, just because we're not good at four-dimensional space, it doesn't mean that it's not, it may be that range could do that if you expose the child early enough. I wouldn't say that's out of the question.
In Link, do you have any, or Vivian, do you have any things for Link to look at that are four-dimensional?
I'll teach
Yeah,
him about
hypercube or something.
quaternions soon.
I was gonna ask, in terms of sort of things that get abstracted away, if I understand Monty at the moment, there isn't an inherent representation of time, as in it's a sampled data system and it doesn't actually matter whether it runs slowly or quickly. It's still essentially ignoring time, just processing a sample and then processing the next sample, and it in that sense sort of synchronous.
Yeah, so the models don't have any temporal dimension at the moment. So I mean, they definitely will need to have it to be able to model object behaviors, for example, or like also melodies and stuff like that. But you're right. Right now, it's on the one hand the property we want. So if I move along this cup, it doesn't matter if I go this direction or that direction. It should be the same. But yeah, it doesn't represent time in the models.
This is a case where I have a pretty solid hypothesis how time is represented in brains and in the cortex, and how it handles the variations in tempo and things like that. So it's not like we're clueless about this. I've talked about this many times. I think I know how neurons are doing this, but it's not in Monty. So, and again, would we do it the same way or not? Is an interesting question. But it is something that I thought about a long time ago, and I figured we've got to solve this problem. And I think I know how brains do it. So.
I was thinking about it like going sort of to the context of control system as like an engineering discipline where like one of the harder things in controlling something as a robot is to deal with delays, and so there's some like temporal problems that have to be solved, but at the same time it's one of those nice things to abstract away and ignore, because the moment you put time into it, then you have to deal with that through your whole system. Like you have to simulate with the notion of time. And
well, you're thinking of time as being a problem, perhaps, because you got delays and things like that.
Yeah.
I was thinking of time as part of the modeling of
as something you have to represent as well.
You have to represent in the model. So it's clear how you have to do that in like melody, and yet you can speed up and slow down the melody and still retain it. It's clear that many of our motor actions, like if I sign my name, there's certain velocities and speed at which my fingers move as I write, and those vary over time. Object behaviors have certain velocities too. And some are faster than others. So as part of the modeling system, it has to represent time and delays. But it's a separate question is, well, then how would if I have to implement this, how do you deal with the variations in the real world? In the brain, there's a lot of suggestions that another part of the brain, the cerebellum, it takes care of that issue of delays and compensating for variations in time, and not the cortex. So again, I don't know what that means for Monty, but
Yeah, and this is a bit of a theme in this presentation too. Like a lot of these things, we have pretty decent hypotheses about how the brain might do it, or even ideas of how we want to implement it, but we just have this huge list of action items and things we need to do to get it into the system. And yeah, obviously, once we actually start implementing it, we'll come across a whole new set of problems too.
fortunately, I think you're sort of at the end of I'm trying to think of what are the big topics that you haven't brought up.
Oh
yet.
yeah, I'll finish up. It's only 3 more. It'll be quick.
You're still
So
on abstract spaces here, yeah.
yeah, I bunched language with abstract spaces. So yeah, just one of the things we talked about before, how we might also, how a language would also be represented in Monty is, so if we, for example, read a sentence, that'll be basic object recognition, like all the other objects are being recognized. We recognize the characters and relative locations of characters from words, which we recognize, but then how do we know what it actually means? We can learn associative connections similar to voting, to models that we've learned in other modalities, like we might have learned a cup with touch, or we've seen a cup, have a model of a cup in a vision learning module, and we can learn an associative connection. So when I read cup, it invokes this model over there. Same with like relative displacements. If I read on, it might invoke like a relative pose, and then table, also the table model, until it like invokes a complete scene in our head. That's at least how it might be working in Monty. And same if we hear language, we would have auditory learning modules that can recognize words given like temporal features.
I think this is sort of the opposite of large language models, in the sense that we start out with these physical models of the world, and we understand that scene, whether we have language for it or not. And then what you're really doing, language is taking this sort of structured model you have there, this compositional structure right now, and translating it into a way of communicating to someone else. It starts with that structured model, not with the language. And where like a deep learning large language model system, there's no physical relationship of anything. It's just the language itself. It's just the words. It's completely flipped around in the brain, and we shouldn't forget that. If we figure out how to represent these structures, essentially, imagine you're looking at that scene and you're attending to different things. You say, oh, there's the table, there's the cup. As you do that, you're forming the representation of the relative position of the cup to the table. That's done visually or tactily. And then you can translate that into language to communicate that to someone. And of course, you can go back the other way, but it starts with those models. And so I think I've always felt that language is a bit dangerous to focus on early, because it's really subservient to having these representational models of the structure of the world first. Otherwise, you end up with like deep learning systems, which are really good at language, but they don't really understand anything.
Yeah, exactly. So the nice thing about this system will be that the language is really grounded in physical reality, and it will really have an understanding of what these words mean and what a cup word is, what is a cup, and similarly also how does this word sound, of course, but yeah, what you said.
Right. Starts at the top, works its way down.
Yeah.
Question. You said grounded in physical reality, but it can also be grounded in abstract reality, right?
Right.
Just
right.
it's whatever the modeled reality is.
Right.
Yeah.
When I say physical reality, what I really mean, there's a reference frame, there's things in the reference frames at orientations and locations. And those could be physical corresponding, or they could be abstract spaces. But either way, you know, it's the same thing.
Yeah.
So the sentence structure there, it looks like, okay, you've got the nouns and the positions of them relative to each other. How do you handle verbs?
Well, those will probably be like behavior models, for example, like object behavior, like we might have morphology model, feature models, and behavior models. And
Okay.
those are the models of how something changes over time that are associated with that.
Your question's exactly what I was trying to address. You start by thinking, oh, well, these different types of words and so on, you're going to get lost. You got to start at the top level, as Viviane was saying, and saying, start with trying to, how do we understand language describe things here? And right, many verbs relate to actions of objects, or actions, relationships between objects. And then verbs come from the reality versus we start with a concept of a verb and try to understand what it is. I mean, I realize there's a big gap there, but that's the way to approach it. Otherwise, you just get lost down the rabbit hole of being linguists.
Okay.
Yeah.
Well, I mean, the notion of a behavioral model makes sense to me. So that you can segregate that functionality into that way of thinking about it. So, okay, I'm satisfied for the moment.
Yeah, let me quickly go over this one. It's not the most interesting one. So deep learning networks suffer from problems with adversarial examples. So you add like a tiny bit of noise and it suddenly makes a totally wrong prediction with high confidence, or a bit more real worldy. You add a little patch on a stop sign and it detects something, a different sign. It's a bit related also that these deep learning vision systems often over rely on texture. So this would, for example, be recognized as an elephant instead of a cat, or this would be recognized as a flamingo or a volcano or an Arctic fox instead of an elephant. Whereas I think Monty would be inherently good at these tasks, or would not be tricked by a different texture on the morphology of an elephant. Obviously, adversarial examples are optimized to the system, so you might optimize adversarial examples for Monty, but hopefully those examples would be more similar to like visual illusions that humans also perceive as visual illusions. That's at least my hope. But yeah, that's something we can explore in the future.
It's hard to imagine how that wouldn't be the case.
Yeah. And then lastly, recognizing objects learned in 3D and 2D. So you learn an object by touching it and looking at it in a three-dimensional world. You have a model of the object and you see a two-dimensional picture of the object and you can recognize it. Or even like a sketched line drawing and you can recognize the object. Yeah, this will, I don't think, be a super difficult property to add to the system, but just another generalization that we might test at some point.
Does Link sign the media release?
I'm his guardian. I get to sign this media release.
Yeah, get some end dimensions into that, maybe test that hypothesis.
Yeah, I think he's actually not so good yet at recognizing the 2D version.
Funny, I didn't see anything else other than a cute baby. Yes. I see Parson wasn't doing very good.
How old?
Almost 9 months.
Wow.
But he's younger in that picture.
Oh, yeah.
This is from today. I made it for this presentation. He's not supposed to look at screens, but I didn't want to print out the picture.
Okay, a little bit.
All right, to sum it up, back to this overview. So these capabilities here, so object detection, accuracy, post-detection, number of steps, speed, noise, and learning unsupervised or continually, those are regularly benchmarked. We have benchmarks in our code base, and you have to update them every time you make a significant change to the code. We have benchmarks in progress for the multiple objects. We have one there already, but I guess I put it in progress because we also still need to solve it, kind of. And then for real world sensors and agents, we also have a basic benchmark there, but also still kind of need to get a decent accuracy on there. And then for compositionality, that's the one we got started on during the hackathon, that we still need to put in like proper accuracy measurements and make it into a benchmark experiment. Current work is focused on dealing with multiple objects and compositionality. And then current brainstorming has lately mostly revolved around different features on the same morphology and object behaviors. And before that, we talked a lot about compositionality, although there we are kind of have some more concrete ideas already on how we want to implement that. And then sometimes we also touch on abstract concepts and how to represent space and reference frames lately.
We're gonna talk about compositionality in a few weeks, right?
Yeah. Yeah. And then there are a couple that are still, like some of them are not as relevant right now, and some of them are still quite untouched, like deformations of objects. Yeah, that was the overview. Anyone have some more questions now?
That was great.
That was amazing.
Yeah.
It really was. I mean, you covered everything. It's like I feel like this is my life. It's organized after 40 years of being disorganized. We've worked on these problems in sort of ad hoc order, you know, because it's so hard to solve them. And for so many years, it was just very, very confusing how these things happen, or even just what had to happen. It took a long time even just to make this list. And yet I think it's pretty complete now. So it's really great to see that.